The previous lecture, we have studied about the types of sampling, and they are ideal sampling, natural sampling, and flat top sampling. And as we have said in the previous lecture, that sampling is the important step for converting analog signal into digital signal. But how the sampling has to be done, for that we are going to study the sampling theorem. So there is some standard way in which the sampling has to be done, and this particular standard way will be following the sampling theorem. So the sampling theorem states that if a signal x of t, which is nothing but our analog signal or a continuous time signal, so if a signal x of t is sampled at a regular interval of time and at a rate higher than twice the highest signal frequency, then the samples contain all the information of original signal. Meaning, there is some signal, analog signal x of t, whose frequency is, let us say, fm, then the sampling frequency, that is fs, should be twice, that is, it is said that it should be higher than twice the highest signal frequency. So analog signal frequency, the sampling frequency should be twice the maximum signal frequency. Then only when the reconstruction of the original signal is done, all the informations will be retrieved. The function x of t may be reconstructed from these samples with the help of a low pass filter. So this is the statement of sampling theorem, that sampling should be done at a regular interval, but its rate should be twice the highest signal frequency. Another definition for the sampling theorem from some different source is a band limited signal can be reconstructed exactly if it is sampled at a rate at least twice the maximum frequency component in it, and both these definitions are meaning same. So the sampling theorem states that the band limited signal should be reconstructed. For successful reconstruction of the signal, the sampling frequency should be at least twice the maximum frequency component into the original signal. So if our sampling frequency is fs and our original signal is fm, then fs should be greater than twice of fm, or it should be equal to twice of fm. So fs should be greater than or equal to twice of fm, then this is called as a sampling theorem. Now first we are going to look of the proof of the sampling theorem, and for that we are going to consider a band limited signal. So this is the band limited signal g of omega with a frequency of minus omega m to omega m, and this particular band limited signal we are going to consider. So we are beginning the proof again by mentioning the statements of sampling theorem. So it states that the maximum frequency component of g of t is fm. Then to recover the signal g of t exactly from its sample, it should be sampled at a rate fs greater than or equal to twice fm, or the minimum required sampling rate should be equal to twice of fm. If not greater, but minimum should be equal to twice of fm. And if this sampling theorem rule is violated, then what will happen, that we will be able to. So when your sampling frequency is exactly equal to twice fm, then this is called as Nyquist rate of sampling interval, Nyquist rate of sampling, and sampling theorem is greater than or equal to twice fm, where fm is the original signal which is to be sampled, and fs is the sampling signal. So now let us consider the proof of the sampling theorem. So we are defining, let g of t be the band limited signal whose bandwidth is omega m is equal to twice of fm. Omega m is equal to 2 pi fm. And I have considered this particular signal g of t as a band limited signal. And if we see the spectrum of this particular signal, it will look like this. where the frequency is from minus omega m to plus omega m. Now let us consider g of t is our original signal, gs of t be the sampled signal, and its Fourier transform is given by gs of omega. So as per the sampling theorem, the sampling frequency fs, which can also be written as 1 by ts, that should be greater than twice fm. This particular statement comes from the sampling theorem. And if we plot this particular gs of t, which is nothing but our train of pulse, which we call it as impulses, it will look like this. So this diagram we have already seen in the impulse sampling. So this is our impulses. If we take Fourier transform of that, then this will be represented like this. So Fourier transform of gs of omega is given by, so Fourier transform of gs of t is equal to Fourier transform of g of t, which is our original signal, multiplied by impulse train. And impulse train is delta t of t. And we have somewhere defined the signal delta t of t will be defined as summation n is equal to minus infinity to infinity delta t minus n into capital T. So that is what, if we substitute n is equal to 0, we get t minus capital T. If we substitute n is equal to minus 1, we get t plus t. If we substitute n is equal to minus 2, we get t plus 2, and because of that we get this impulse. So this is nothing but our sampling, wherein we are multiplying g of t and a sampling signal. So substitute the value of delta t, which we have defined here, into the equation 1. This is equation 1. So substituting the value of delta t will get g of t into summation of n is equal to minus infinity to infinity del of t minus nt. Now this is, we are going to take Fourier transform of this. This is complete time domain. We are converting into frequency domain. So taking Fourier transform, multiplication here will be converted into convolution. So Fourier transform of gs of t is gs of omega. Fourier transform of this complete is 1 by 2 pi. G of t, it is g of omega, multiplication to convolution, and Fourier transform of impulse will be omega 0 into summation of n is equal to minus infinity to infinity del of omega minus n omega 0. This is our equation number 2. Now if we take this omega 0 outside and substitute omega is equal to 2 pi f, so what we get? Omega 0 divided by 2 pi is equal to 2 pi f naught divided by 2 pi. So this 2 pi and 2 pi will get cancelled. F naught is equal to 1 by t, and substitute this in equation number 2. So what we'll get is gs of omega is equal to 1 by t summation of n is equal to minus infinity to infinity g of omega convolved with del of omega minus n omega 0. So convolution of this particular term is nothing but shifting this particular frequency. Convolution of g of omega into impulse is nothing but shifting this omega by omega minus n omega 0. So what will be the convolution of this? Convolution of this will be 1 by t into summation of 1 by t into summation of n is equal to minus infinity to infinity g of omega minus n omega 0. So simply the formula for the convolution is applied. Multiplication of g of omega and del of this is nothing but omega shifted by omega minus n omega 0, and that is what we get this particular equation. So this is our proof of sampling theorem. So how we have done the sampling theorem? We have considered our original signal g of t represented in the frequency domain, that is represented in the frequency domain, and it will look like this. Then we have considered a sampling signal whose frequency is greater than twice fm, which is nothing but impulse train. In frequency domain it will look like this. Then simply multiplying del of omega and g of omega will give us this particular equation. Then taking Fourier transform of this, multiplication in the frequency domain is convolution, and convolution of g of omega with del of omega minus n omega 0 is nothing but shifting omega by omega minus n omega 0. So this is nothing but our final statement of the convolution final statement of the sampling theorem, and this is what is the sampling of the band limited signal. Now we said according to the sampling theorem, the sampling frequency should be greater than twice fm. If this is not means if the sampling frequency omega s is less than twice omega m, then what will happen? Whatever samples which we are getting at the output, they are going to overlap with each other. You see clearly, this is sample 1, sample 2, sample 3. They are overlapping with each other, and this particular effect is because of interference of high frequency component. So when you are not following the sampling theorem, means your omega s is less than twice omega m, the samples are overlapping in the frequency domain, and this particular effect is called as aliasing effect, which is happening because of inadequate sampling. And that is why, to avoid this aliasing effect, the sampling frequency should be greater than twice of fm. If this rule is violating, we get overlap in the sample, and this is called as aliasing effect. And if oversampling is done, means in practice the signals are oversampled where fs is significantly higher than Nyquist rate, then this is going to avoid the aliasing effect. You see clearly, if your sampling frequency is very high then your Nyquist rate, then aliasing effect is avoided. The samples are equally spaced, whereas in the previous you can see there is a overlapping here, and this is called as aliasing effect when sampling theorem is not followed. So this is called as undersampling, this is called as oversampling, and when you do sampling exactly equals to Nyquist rate, you will be getting a samples which are exactly touching to each other. That is, your omega s is equal to twice of omega m. If omega s greater than twice of omega m, then aliasing, then aliasing effect, and if omega s is much greater than the omega m, then you will be getting oversampled signal. So this is what is the proof of the sampling theorem, which states that any signal which has to be converted into a digital signal, the sampling of the signal should be done at a rate twice the maximum signal frequency, and if not, it is not done, then aliasing effect will be there in the output, and the reconstruction of the signal is difficult.